We have an extreme lesson today. So much so, 2 letters get replaced with just an X. Extreme. All right. What did you take away from the videos? What were the main takeaways? Maximums and minimums. Global. Which global and absolute are synonymous. Local and relative are synonymous. So if you see, find the absolute maximum value of the function, same as saying find the global maximum. All right. Local. How would you define a local?
It's within a set domain.
Okay. Within a set domain. And let's say we have a local max. We've used the analogy of the pandemic before, right? And it's like, okay, it started off like this. Oh, glitchy.
It's the tabs.
Mind your own tabs.
Close them. Close them. Yep. Close them. Maybe we should just take a mental health day for the tabs today. Clear.
Every day's a mental health day for you. So it went up last October, came down, and then in December again, it got extreme. All right, went back down, back up. All right, let's say that is the curve. Now, this is not accurate. This is not quite as high as that was. But if you were to classify these, you're probably going to say that's a maximum. And Cole used a good analogy he said on a domain. So if we remember, do you remember what on a domain means? On a smaller domain. If you were to they're going to love that on the video. They're going to be sitting there and be like, I need a minute. Better pause. Watch that again. All right. On a window nearby, that's the highest point. You don't know if it's the highest point unless you open the window and look around. Okay, you're like, oh wow, I thought that was high, and then I saw this over here. That is absolutely the highest point on this graph. Do you agree? Right there? Rest of them? Local. Rest of them? Local. How about these points? Low. And to find out if they're the lowest, the absolute lowest, you'd have to actually plug them in and verify what's the minimum value there. Make sense? I'm trying to remember in the video, did they explain in a calculus way and an algebraic way how to collect all of these possible high points and low points? Where do they come from? Where do they go? Where do they come from? Where could they come from? Did they explain this? Help me out, I'm blanking. Did they explain where the points can come from? You tell me. On a closed domain, so let's say we have from -5 to 5. From -5 to 5, I give you a function and I say list all the maximum and minimum values, both absolute and local. How could you collect all of them without a graph? Like, I'm going to graph it, yes. But if you're given a function and you had to collect them all, where do they come from? Look.
Take the derivative and so we go to 0.
Perfect. They can come from f prime of x equaling 0. What happens when f prime of x equals 0? Horizontal tangent. So let's say I say, okay, there's a horizontal tangent here on f of x. I just drew in the tangent line. What could the function look like there if it has a horizontal tangent? What could happen? Adam. Had your hand up. I like your color scheme today. Looking nice. Looks comfortable too. Matching shoes and everything. For those at home, he's wearing looks like a plaid. What do we say that? What do you call it? Plaid flannel, unbuttoned with a thermal underneath that's brown colored. Very comfortable. He's sitting in a relaxed position. He's ready for calculus. What do you think, Adam? You don't know. Luke's gotcha. Luke, you got this?
So what was your question? I was thinking about his outfit.
It's okay. All right. If a function has a horizontal tangent, what could be happening on the graph?
Slope equals 0.
Right? So draw it in the air of a function that has a slope of 0 at a point. Yes. Nice. I like it. Option A. Do you agree that could happen? Yeah? Gavin, give me another option of what the function could do. Oh, he went there.
No.
Up. Horizontal tangent. Just kidding. I'm going up. Was that what you're drawing? Thank you. Appreciate you. Last example. Kind of. Avery, what do you think? Yes. It could have been a that. And then, of course, it could have gone down the negative of Gavin's graph. Yes? Do you agree all of these are possible situations when you have a horizontal tangent or when the derivative equals 0? Okay, this is still prepping for the lesson. Are you ready for this? These are smooth, possible extreme values. Okay? Because if you set the derivative equal to 0, what are you going to get? You set the derivative equal to 0. You're going to get the x value where that happens. Do you agree? But you don't. Without a graph, you don't know what it looks like. Or do you? How can we find out whether it's the Luke example, the Gavin example, or the Avery example? How do we figure out which one it's going to be from the equation, from the derivative? We have this x value because we set the derivative equal to 0. We have the x value. Cool.
Look at the derivatives approaching that point.
Yeah, okay, let's do it. Ready? Red one was first, wasn't it? No.
Yeah, that was first.
Red was first? Okay. Eyeballs on the red one. Eyes on the red graph. At that x value, f prime equals 0. Before that x value, f prime was on. So the red is f. What's f prime? Huh? Positive. Look on the red graph. Positive slope, getting close to 0 slope. Yes? The red f prime at that x is negative. Nope, positive. Do you agree? I was getting ahead. Oh, spoiler alert. How about after that x value on the red graph? Negative. F prime is now negative. Okay, so pretend you can't see it. You plugged in 2 x's into the derivative. You knew at that x value it was 0. Before the x value, f prime is positive. After, f prime is negative. What happens to an f graph when its derivative changes from positive to negative? Well, I was going up, and now I'm going down. There was a maximum there. Do you get that? Jackson, you good? Make sense? Well, let's look at the next example. The green one. The green one before that x value where the derivative was 0, f prime was, what are f primes on this green graph? Negative. And then after, f primes are positive. I was going down, horizontal tangent. Now I'm going up. We would call that a minimum. Minimum. We don't know what kind yet. We can't see everything in the picture yet. But on that window, it's a minimum. Ready for the Gavin example? Before x that gave us the horizontal tangent, f prime was positive. After, f prime is, oh, that's cruel. I'm going up, 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 up. Horizontal tangent. Just kidding. Up, 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 up. This sounds familiar. This test that we're doing right now in the derivative sounds like what's that?
Behavior.
Yes. Good. Wasn't expecting that, but that is 100% accurate. What else? Sounds like. We should do charade calculus.
Pointing.
Stopping. Backwards.
A change in. When I was walking in front of the room, my velocity was negative, 0, positive. I changed direction. My slopes are negative, 0, positive. The graph changed direction. Do you see it? Do you hear it? Ready? Red one. My velocity was positive, 0, negative. I changed. Close your ears. This seems to be surprising.
Should I take the other part now? Or
You want
should I
to?
just wait? I can't.
I think so. Keep the roll going. You have a roll? No calculator?
Look at you.
Is that, didn't you say it's pretty easy? Yeah. It's just the derivative rules. That's it. That's all. All right. We call him the sensei. Second period. All right. Do you guys hear the difference? Do you hear, not the difference, do you hear the connection? Ready? I was walking to the left. I stopped. I kept walking to the left. Did I change direction? No. Blue graph. Only in this case, I was walking to the right, stopped, kept walking to the right. Okay. That was a lot of words to explain when the derivative equals 0. We could have. Blue, don't necessarily have to have a max or a min. But we could have a max or a min when the derivative equals 0. Do you agree? But we have to test it. We have to test it. What's another scenario of where a function could change directions? Sorry, that was French. Directions. Directions. What's he doing? Why is he doing that? What else? You see something there, don't you? You see it? Oh, it's hard. What else? The function could change direction at a corner. Yeah. Could it change at a discontinuity? I don't think so. I'll have to think about that. A jump. I wouldn't say that's a change in direction. Like, I can't be walking to the left and then magically appear over here. I wish I could. And there's times you get into an awkward conversation with, a coworker. They're like, "Oh, I'm out of here." Jump this continuity to the lunchroom. To the lunchroom. That'd be awesome. Love it. Mr. McCoy.
Oh.
I'm just kidding. All right. A sharp change in direction. Do you agree? A sharp change in direction. All right. Gavin, the emergency bucket's back there in case you need a Band-Aid. All right, just so you know. All right. Could you have a sharp change in direction? Yeah, but the derivative is not going to equal 0. The derivative does not exist at this x value. Ah. So what if you take the derivative and you're like, the derivative doesn't equal 0, but it doesn't exist there. Should we still test it for a max or a min? Yes. Do you agree there's a max on the green? There's a min on the red. Do you agree? How would you find that? Well, the derivative. The derivative doesn't exist at this x value. Before that point, though, the derivative is positive, doesn't exist, then negative. Ah, the derivative changes sign. How about the red one? The derivative is then, yeah. Oh man, I wish I had a ton of time. This, I just learned for the first time where the cusp comes from. It's incredible. It all ties into that Berkeister-Crone curve that we talked about. Isn't that crazy?
That's cool. Where do you learn?
On a video, Vsauce. Michael here. So the cool thing about it is, if you trace out, if you take a wheel from the center and you have like something attached to it, and you take that point on the circumference. Don't get too comfortable here.
That's my wallet.
Okay, right there.
Thank you.
You're welcome. You can thank Jake.
Thank you.
If you have a wheel and you trace out a point on the circumference of the wheel, do you know what curve you get? Well, spoiler. Ready? Ready? Can you see it? Watch. Can you see it? It's called a cycloid. Okay? It's called a cycloid curve. It creates cusps. All right? Now, when you take part of that curve and you get rid of it, the curve that you're left with is the Berkeister-Crone curve. It's a part of a cycloid. Cusp. You could also get it from the absolute value of sine of x, I think. Nope. All right. Well, last scenario. Where could extreme values come from? Well, when the derivative equals 0, it's a possibility. When the derivative doesn't exist, it's a possibility. And if it's a closed interval, aren't endpoints going to be high points or low points? Just like calculus in your day. It's a high point. It's the max of your day. Well, what if the graph starts here and goes up? Then that point is a minimum. If it starts here and goes down, that point is a maximum. We can't test to the left of a left endpoint. But I have good news for you. We can test on this side of it. Ready? What happens if I plug in this x value right here and I get positive derivative? Positive derivative, the function's going up. And if you go up out of a point, that point is a minimum. If the derivative is negative, I start at an endpoint and I go, the derivative is negative, I'm going down. That point's the high point. Do you agree? this is what we're working towards. It's called the first derivative test for extrema. And it considers all of those points, both endpoints, smooth changes in direction. Are you done already?
Yeah.
This is not okay.
Sorry.
You better be.
Oh, okay.
Did you get past?
No, it's scribbling.
I'll see you later.
Before I ended, he was done with both.
Can we get bonus points for speed running the test?
For speed grading?
Speed running.
Oh, speed running? Like parkouring through it?
Yeah.
Jump from one problem to the other.
Less
Yeah,
work is
so
possible.
Anyway, so we would call this a local max. It's hot. It's higher than this point, right? We call this one a local min, local max, local, local, local. Absolute max. Very good. Very good. Made me proud. Now you get to look at this graph. You get to look at it. All right. So we're not going to be able to look at these. We're going to have to use calculus to determine. Now, where could all the max and min values come from without a restricted domain? In other words, the domain's now all real. What's your inkling? Do you think every function is going to have an absolute max and absolute min? What about a parabola? Absolute max? No. Absolute min? Yes. So it could have both. It doesn't have to. Is there an example where a function, I think this is in the video, is there a function that has no maxes or mins? I think she had it in the video, right? Or he?
Just a horizontal line.
Oh.
What's that? Both the max and
It could be both the max and the min. That's a thinker. Casey? Oh. Yeah, so those are special cases that we're not going to even really get into. Are you ready for this? Any absolute max or mins on that? You think so? Dom's getting after it. There we go. Let's say this is a y value of 2. Let's say this is a y value of -1. And let's say this is -2. Let's say this is down here at -3. Go for it, Dom. What do you think?
the absolute min would be as you approach -3.
Absolute min would be -3.
It'd be as you approach -3.
So what is it?
2.9.
Huh?
2.9. -2.9.
I can give you another number that's lower than -2.9. Whatever he left off at, I'm gonna add one more number.
But it's repeating.
There's different levels of infinity.
How can you have done
Okay, a carpenter's building chairs. Okay, classic problem. There's also an analogy with rooms. A carpenter, man, they're missing this concept. I don't know. A carpenter builds chairs. For every 4 chairs he or she builds, they break a hammer. Okay? They build infinitely many chairs. How many hammers did they break? Infinitely many, but less.
That's true.
A lesser infinity.
Well,
Merry Christmas, Mrs. Smith.
It's just a plant for a few more days.
Oh.
It's just a plan.
Do you know the different levels of infinity?
I know infinity and beyond.
Oh, Buzz Lightyear.
Well played, right?
I like it.
Yeah. No, I do not. Sorry.
It's okay. We'll forgive you. How about debt? National debt.
She's walking away.
She said yes. All right. Do you agree there's different levels of infinity? And technically, I could prove that negative 2.9 repeating is equal to 1.
Huh?
That's a lot.
Bonus content. You guys get me off topic.
I want to see this.
What? How does it equal to 1?
I'll do it in a different way. Using your argument, 1/3 is 0.3 repeating. Do you agree? What's 2/3? 0.6 repeating. What's 0.3 repeating plus 0.6 repeating? 0.9 repeating. Do you all agree? But 1/3 plus 2/3 is 1. Therefore, 0.9 repeating equals 1.
Well, what do you have to say now? So,
Tom's wrong. So
I didn't say he's wrong. I just showed you an example.
So then why would 0.3 and
who's full ever guess? That's good.
0.6 be considered 0.9? Why would they call it that if it's not equal to 0.9? Or if it's not equal to 1? Why would 1/3 be translated to 0.3? and
That's what we
2/3
do,
be
right? We
translated
write-
to 0.6?
We say how many times does 3 go into 1? We say 0.3 repeating when we turn it into a decimal. Right? 0.3, the 3's go on forever. 2/3 is 0.6 repeating. 6 is go on forever. Doesn't that make 0.9 repeating? But that's 1. 1/3 plus 2/3. I mean, you have a third of a pie and 2/3 of a pie. You have a whole pie. Question.
What if it was like, what if it was like infinity minus 1 over infinity all over infinity? Wouldn't that be like the closest you can get to 0.99999?
Infinity minus 1 over infinity,
Yeah, all over infinity.
all over infinity. Is infinity over infinity 1? I don't know, because what if they're different levels of infinity?
Oh.
I would say it's indeterminate. It's getting deep here, isn't it?
Can't you say it has a slope though because it's negative 2.9 repeating is defined on the graph. It's only negative 3.
It is. Negative 2.9 repeating on the graph is defined.
Yeah, because it ends at 3.
How big is a point? Because that open circle is a point.
Yes.
How big is a point?
Infinitely small.
Infinitely small. If it's infinitely small, how close can you get to it? Infinitely close.
Yeah.
So what's infinitely close to negative 3?
2.9 repeating.
I can get closer.
The lower as you reach.
To infinity 1 over.
I'm not. No, this is not like. This is good conversation. He's the one brave enough to stick his neck out and argue it.
Bro, I wouldn't even know what to say.
See what I'm saying?
I guess.
If I put this on a number line, if I put it on a number line and I say here's here's 0, here's negative 3. There's an open circle. Give me the closest number you can get to negative 3. We've never, I don't know that any teachers ever really explained the real number system in its entirety, but the real number system has infinitely many numbers on it, right? Whole numbers, fractions, positive, negative integers, and their proper fractions, improper fractions. Irrational numbers as well. So we're talking every single number on that number line is listed. And so if you say negative 2.9 repeating, by the definition of the real number system, there has to be infinitely many numbers between negative 2.9 repeating and negative 3. Hello, Mrs. Peters.
I didn't expect to see high school students here.
I didn't either.
Nice looking group. At
Some.
least these are good looking.
Don't you like Adam's look today? He's got the fall vibe going on.
How much hair has he grown this
A
year?
lot.
Like it's a, kind of we could measure it and do an equation or
Okay.
graph
Get
it.
Yes.
a haircut tonight.
Infinitely amount.
I think let it grow a little more. You could do lost for love and donate it because you have good hair.
I appreciate
I
that.
see that.
Yeah, so do we. You know, just good hair. Sorry to interrupt.
Oh, anytime. You looking for Mr. DeGeorge?
I was.
He's relocated.
Where is he?
124-ish.
Ish. Thank you.
Infinitely close to room 124. She's gonna approach it really close, isn't she?
You can approach it closer.
Hopefully. That was the comfort that led to that answer.
Like,
See, Richard does understand. He knows when they're somewhere.
Anyway, moral of the story, there's no minimum in this graph. There's no minimum value that can be defined. There's no maximum value on this graph that can be defined. Isn't that crazy? Wow. You came to Calc excited for this kind of conversation, didn't you?
Why are you still looking at
All right. We need to get into some actual math. So the moral of the story, your extreme values are going to come from endpoints, possibly endpoints. Smooth changes in direction. What do I mean by smooth changes in direction? Well, that's where the derivative equals 0. Not sharp, it's smooth. Derivative equals 0. Smooth changes in direction or sharp changes in direction. Those are going to be the candidates that we consider for extreme values. But just to get us thinking about it, let's take a look at this function right here. 1 over the square root of x squared minus 1. Do you know what the graph looks like? Do you know what that graph looks like? Good. Okay. What's the domain of this function? This is always a great exercise to start off with, is finding the domain of the function they give you. Because wouldn't the domain tell us if it has any endpoints? And where it exists, right? What's the domain? Write this down. What's the domain of this function? What are the rules you've been taught about domain? Denominator can equal 0. I like it. Square roots can't be negative. I like it. And this is a combo, isn't it? And not like the disgusting combos that you eat in a snack pack. Those are terrible.
those are
Amazing.
all-
If you get the pizza,
It's like flavor powder inside of a pretzel, which pretzels are overrated. All right. I'll stand by that. X squared minus 1. Do you agree x squared minus 1 in this problem is in the denominator and inside of a square root? It's got to be really careful. You okay?
Is it x squared or
It's x squared. X squared minus 1. Let's make a rule for x squared minus 1. It has to be, to find the domain, x squared minus 1, the inside of the square root has to be positive, greater than 0, greater than or equal to, just greater than. If it were just a square root, if it were a square root in the numerator, we would say greater than or equal to 0. Because you can have a 0 inside of a square root. It's in the denominator, so it can't be negative and it can't be 0. Agree? So our domain is x squared minus 1 has to be greater than 0. When is x squared minus 1 greater than 0? Do you know this or do you need some refresher? You did this back in Algebra 2 honors. It was called quadratic inequalities.
all values greater than 1? And less than. And less than 1.
I was going to say you were halfway there. Or if there's infinitely many numbers, you're actually not even close to the way there.
back on this again.
All right. You were taught. Okay, we're gonna get a little Inception here. Okay, have you seen the movie Inception? Mind-boggling. You think you understand things and then you don't understand things at all. Okay. Anyway, do you know how there's going to be a test to find out where the high points and low points on the graph? A test, right? Like test before the point, test after the point. There's also a test to find out where x squared minus 1 is positive. You did this in algebra 2. Okay? Here's what you did. You set x squared minus 1 equal to 0. Okay, x equals plus or minus 1. Do you agree? Plus or minus 1. You put those on a number line. You tested points before, between, and after. And then you put, did you put little plus signs and minus signs there? Okay, so here we go. Plug in negative 2. Negative 2 squared. 4. 4 minus 1. Is 4 minus 1 greater than 0? Yeah. So did you put a plus there or did you put a yes? Plus? Plus. What does that plus mean? That x squared minus 1 is positive before negative 1. I only had to test one number. Why? Because if it was going to change again, I would have had another critical value, critical number. I think you called them. Yes?
Yeah.
Next, plug in 0. 0 squared minus 1. Is negative 1 greater than 0? No. So that must have been where the function was negative, and then 2 squared minus 1, positive. Now here's the key, and I don't know if Mr. Laverick and Mrs. Nepholtz overlaid the graph with this test. You guys know what the graph of x squared minus 1 looks like. Parabola opening up. Down 1. Didn't mean to curtsy. Sorry. Down 1. That was embarrassing. You didn't see that.
We'll do that one at that problem.
It's a good thing you guys didn't see that. Do you agree that's what the graph looks like? Now, can we confirm? Is x squared minus 1 greater than 0 here? Yes? So what intervals are those? Well, x is... Oops, I shouldn't have done that. I was getting distracted by my curtsy. Open circle. Open circle. X is less than negative 1 and x is greater than 1. Or negative infinity to negative 1 union 1 to infinity. What does that mean? That is when the graph of x squared minus 1 is greater than 0. Wait a minute. That means something in this problem. We looked at that graph to find the domain of this function. Isn't that weird? I need you guys to ask if you're confused. Does that make sense or is that weird? Or both? Does it make sense and it's weird? Do you understand what I just did? I tested to see where x squared minus 1 is greater than 0 because that's where this function will even be able to be graphed. So what's the domain? Negative infinity to negative 1. 1 to infinity. I have good news for you. When we go to do this problem, if we were to find the max and mins of it, are there going to be any extrema between negative 1 and 1? No. Because you can't have a high point or a low point on the graph if it doesn't even exist there. Do you agree? All right, find the first derivative. That's our second part of the problem. I don't like it like this. I'm going to write it as x squared minus 1 to the negative 1/2 before I do any calculus on it. Do you agree? I don't want to do a quotient rule. I just don't feel like it. F prime of x. Negative 1/2. Leave the inside alone. Subtract 1 from the exponent. Negative 3/2. Times 2x. Don't forget the chain rule. The 2's cancel. we get negative x over x squared minus 1 to the 3 halves. This is the moment you've all, actually none of you, have been waiting for. I told you a long time ago, we're going to write our fractions, our derivatives, as one fraction with positive exponents, because there might be a day when we have to set it equal to 0 and find out where the denominator doesn't exist. Today is that day. Are you ready? I've got a big meeting.
Computers.
Big meeting. It's going to get intense. All right. Well, we did what it asked us to do. But what if I had a classroom full of excited calculus students that said, let's set it equal to 0. Let's find out where it doesn't exist.
Let's do it.
What if?
Let's do it.
What if? Well, the only time a fraction can equal 0 is when its numerator equals 0. So when does this derivative equal 0? This is the derivative. It equals 0 when x equals 0. Wait a minute. X equals 0? That's not on the domain. It's out. Why? It's not on the domain. It's not going to be where the graph even exists. What else? When does the derivative... So wait a minute. Back up. When the derivative equals 0, what could happen on a graph? Not this one. Other graphs. When the derivative equals 0, you could have... What kind of changes in direction? Possible. Smooth changes in direction. What about when the derivative doesn't exist? Either the function wasn't continuous or it was sharp. Can you have a high point or a low point at a sharp value? Yeah. Or maybe it was like an end point. Maybe your derivative didn't exist because it was on the edge of the graph. You couldn't approach it from the left or the right. Okay. Well, this is the derivative. Where does this derivative fail to exist? When the denominator is 0 or negative, right? Because it's a even root. It's an even root. Can't be negative under there. When does this derivative equal 0? When when the denominator equals 0. When x is... We've already done that. When does this equal 0? Negative 1? Positive 1. Those are the only points on this graph where the graph could possibly have a high point or a low point. I bet you want to graph it, don't you? 1 over the square root of x squared minus 1. 1 over. Does anybody know what this looks like? 1 over the square root of x squared minus 1. Anyone? Give me a little arm motion if you do. Show me what it looks like. What do you think? Yeah, you can guess. Yeah. I like the moves. Not bad. You take a stab at it?
Something like that.
Hold it up proud.
Oh, nice.
Probably kid style?
Something like that.
This thing's so slow.
I wonder why it's
You're not
slow.
going to see my tabs on the calculator.
I wonder why it's slow.
I wonder why you're slow.
Yeah.
I just got
How's recognition night last night? We might not.
Uh-oh.
Gotta get that homework in. You guys are gonna have a really short homework. And it's just gonna be analyzing graphs.
No.
Alright. You're gonna see my tabs. I apologize. Please don't judge. Tuesday. Alright, we're gonna do 1 through. Don't do the quick review. Most of the page that this starts on is quick review. Don't do it. Go down to the dark blue exercise section. All right. We're doing 1 through 4. Let's just call it that. Let's say 1 through 4. That's it. Just the graphs. Yes. If you want to stay for the bonus content. Graphing the original. That's not it, is it?
You're right.
Was that it? No, it was one minus X. Was it X squared minus 1?
That's right.
You guys see how it does not exist between -1 and 1? Isn't that crazy? This graph has no extrema. I could graph the derivative.
See that? Yeah, I think it's like this. But I don't really know.
Nice.
A little off.
It's okay. It happens to the best of us.
Yeah, wait, how can you find negative infinity to -1, 1 to infinity? What if they're different levels of infinity?